I am Jenny Sanders, and this is Lab 5. The objective is to understand the motion of falling objects involving the force of gravity and the drag constant for each object. I observed the motion of a fast-falling object and a slow-moving object, recording the positions at each time interval. I then compared these measurements to what my computational models observed after I altered the drag constant for each object. So the first thing I did was in Tracker, I uploaded the videos and set the time period by moving these black arrows right here. This is the video for the water bottle. So here's the time period. Here it is 0.5 seconds in time. I set the origin at the center of the water bottle, and then here I set the other one at the koozie, center of the koozie. I chose to have the objects moving in the negative x direction, moving the axis this way. As you can see, here's my video. I took the center of the object as the average position, starting right here, and then moving this way as it went down. And I found the position at different times. As you can see on this graph, I did the same thing for the koozie, right here. And this time length of this one is 0.7 seconds, as you can see in this chart right here. I set that diameter at the beginning of the objects with the calibration stick. Right here the water bottle is 0.1 meters and the koozie is 0.02 meters right here. The next thing I did was then I moved this stuff to computational model. Hold on. So the first thing I did was I looked at each one only being affected with gravity. For each model I made, I set the mass of the object. Hold on. The mass of the water bottle is 0.25 kilograms. And then, so I set that for each of them. The other one is 0.085 kilograms. I set the initial position as 0. Right here, and the initial velocity, because it's just dropped from my hand, as 0. The time step was 0.01. I went from the time is less than 0.5 because that's what I got in Tracker. That's how long it took. I took the gravity is negative 9.81, and I found the force of gravity is that times the mass. Using Newton's second law right here, I said the ball's velocity, the final velocity, is equal to the initial velocity plus the force, which in this case is just the force of gravity, divided by the mass of the ball times the change in time. I did the same thing for the koozie. Wrong one. As you can see right here, the mass is 0.085 kilograms, initial position is 0, initial velocity is 0, delta t is 0.01, time is less than 0.7, because in this case in Tracker it was 0.7 seconds, gravity is negative 9.81, force of gravity is only the gravity times the mass, and the same thing, the Newton's second law is right here. So then I ran these models. And I got the water ball with gravity. Right here is the Tracker. So the Tracker is in the red, and then the computational model is in blue. So as you can see, this is just only affected by gravity, and it's not exactly the same. And I did the same thing with the koozie. And as you can see, it's not the same at all, with only the gravity being affecting it. The red one's the Tracker, the blue one's the computational model. So then I changed the drag for each one. I'm going to go to the water ball's computational model. I kept the initial position, initial velocity at 0, delta t at 0.01, time less than 0.5, gravity negative 9.81. I did the same thing right here, but the only thing that changed was instead of the force of gravity only being the thing that affected the force of drag was also included. And I found the drag constant as 0.115, and I used the equation, the force of drag equal to the negative drag constant times the magnitude of the velocity times the velocity of the ball. I did the same thing with the koozie. Kept everything the same except for the drag force. Did the same thing, except this one was a bigger drag constant. It was 1.3. So I'm going to show you the graphs that came after. So this is the red one's the tracker information, the blue one is the computational model. As you can see, they're pretty much identical. And then with the slower moving koozie, you can see it's closer than it was before. Red one's the tracker, blue's the computational model. And yeah, and that's how it's affected with drag as well, not only just gravity. For the what does it mean question, I took the velocity. I did a computational model and just found the velocity, whatever. And as you can see, the blue one is affected just by the gravity, and the red one is affected just by the drag as well. And you can see that the koozie one, the slower moving object, actually reached a terminal velocity due to the drag, unlike the one that was just affected by gravity. So to answer the what does it mean question, with the velocity versus time model, the model with the drag actually resulted in a terminal velocity of negative 0.8. With the what if question, we looked at an object if it is not just dropped but propelled with a downward velocity, and the same thing occurred. The red one's with the drag, the blue one is with just the gravity. The red one actually ended up having a terminal velocity just like the other one. So if an object has initial velocity, unlike the other one, it will still have a terminal velocity. These models have shown that a falling object's motion is affected by gravity and drag. So as you can see, the ones with the drag looks just like the tracker information.